All right, let's do this. Let's do some degeneracy pressure here, shall we? So from last time, we said here's the condition for finding the value of the Fermi radius, K Fermi, that we see how many states there are in K space, such that we put all the particles in the lowest possible energy they can go into. And so we've got the factor of 2, because 2 particles in each state. 1/8 times 4/3 pi k Fermi cubed is the volume of this octave of the sphere of radius K Fermi in K space. And L over pi quantity cubed is the number of states per unit volume of K space. So we multiply all those things together, and that should be equal to the total number of particles that is in our box. And so now we've got everything we need to solve for K Fermi. Solving for K Fermi cubed, this says that, well, 2 times 4 divided by 8, those cancel it. And so we get that K Fermi cubed is going to be equal to 3 pi squared times number of particles over L cubed. Because here we got pi over pi cubed. So we would have a 1 over pi squared over here. Multiply it through to the other side. We get that pi squared there. This 3 in the denominator is the only numerical coefficient that survives on the left. So it comes in as a 3 on the right. So K Fermi cubed is 3 pi squared times the number of particles divided by L cubed, where remember that our particles are in our cubical star, which is a cube of psi L on each side. So N over L cubed, why, how would you interpret that? That's the number of particles divided by L cubed. What is L cubed? That's the volume of the box, right? So N over L cubed is little n, the number density, the number of the fermions per cubic meter inside of our box. So we could say that this is equal to 3 pi squared times little n, where little n is the particle number density. Particle number density. So notice that it just depends on that ratio. It doesn't depend really kind of separately on the number of particles and the volume of the box. It depends on the number density. So if I make the box twice as big in terms of volume, and I put twice as many particles into it, the Fermi radius would be exactly the same in both cases, because all that's needed, that we need to know, is the particle number density. So it's nice that that draws it out. What questions do you have at this point? And so now we want the Fermi energy. That's the energy of particles whose K is equal to K Fermi. The Fermi energy is then, we'll call that E sub F, and that'll be P squared over 2m. But K is the wave number, and in terms of the wave number, what's the expression for the momentum in quantum mechanics? Remember? So what's the de Broglie, however you say that name, relation? What's the relation between momentum and wavelength? What's the de Broglie relation? P is h over lambda. P is h over lambda. Okay. So let's see. Lambda. How's lambda related to K? Yeah, the lambda is 2 pi over k, right? K is 2 pi over lambda, lambda is 2 pi over k. So this is going to be hk over 2 pi. Since k is 2 pi over lambda, so 1 over lambda is k over 2 pi. And if only there was a special name for h over 2 pi. That's h bar, right? That's h bar. So this is h bar k. Burn it into your brain. P is h bar k. P is h bar k, because that just shows up in quantum all the time. So E Fermi is P Fermi squared, we could call it over 2m, the momentum of a particle that has k equals k Fermi as its wave number. And so that's going to be h bar squared k Fermi squared over 2m, because these are non-interacting particles in a box where the potential energy is 0 inside the box, so their energy is all kinetic energies, momentum squared over 2m. And if you're on the Fermi surface in k space, in terms of your wave number, then your energy would be h bar squared k Fermi squared over 2m. And so this says, now that we know what E Fermi, what k Fermi is, well, k Fermi cubed is 3 pi squared n. And if I want k Fermi squared, I'll say, so k Fermi squared, since that's what we're doing, k Fermi squared is, well, we know what k Fermi cubed is. What power do I need to raise that to get k Fermi squared? K Fermi squared is k Fermi cubed to what power? 2/3, right? If I raise it to the 2/3 power. So E Fermi, which again is h bar squared k Fermi squared over 2m. Well, I just put my expression over there to the 2/3 power, and I get h bar squared over 2m times 3 pi squared n to the 2/3 power. Ta-da! That's the Fermi energy. So it depends entirely on the particle density, what the Fermi energy is. Number density of those fermions tells us what the Fermi energy of them is. And remember again, the Fermi energy is the energy of the highest occupied states at t equals 0. Because we put everything in as low a state as we can, put all the particles in the lowest energy state available as we add them one by one in our imagination. So this is the ground state that we're in, and the most energetic particles in the ground state, t equals 0, will be the Fermi energy. What would the energy of the particles be classically? See if you're remembering this, or I don't know. What you've done in thermal, I ain't teaching it. Classically, at t equals 0, what would the thermal energy of the particles be? It would be 0, right? Classically, they'd have 0 energy. Quantum mechanically, nope, they have the Fermi energy. So obviously, at t equals 0, the particles have a lot more energy than they would classically. What about at other temperatures? I've said this before, but let's kind of formalize it here. For t being greater than 0, if the Fermi energy is much, much greater than kT, which is the classical thermal energy, and I gotta be careful. So at this point, I'm going to be, it's K sub B, right? In honor of Kathleen, right? Again, that's right, yes, KB over here. To emphasize it's the Boltzmann constant versus the K-space wave numbers, right? So we need to be careful here. So Boltzmann constant times the temperature is a good estimate of the typical average energy of a particle in thermal equilibrium classically, that's the roughly 3/2 kBT if it's an ideal monatomic gas, etc. kBT is on the order of the typical classical thermal energy. If the Fermi energy is much greater than that, the classical thermal energy, typical energy of a particle, then the Fermi energy greatly exceeds the thermal energy. It's a little repetitive, I'm just trying to be clear here. The Fermi energy is much more than the thermal energy. This is the case where, for most of the fermions, their energies, because they're out in k-space, far from the origin, where the energies are much greater than the thermal energy, most of the particle's energy is due to the Pauli exclusion principle in a sense, because they've been forced into high energies by the fact that how many electrons can go in each spatial state? Just 2 of them. What has to be true about them? Opposite spins, right? You have to have opposite spins. In this case, the energies of almost all the fermions as a result of the Pauli exclusion principle. In this case, the energies of almost all the fermions, the lowest energy ones down near the origin, not necessarily, the energies of almost all the particles. And again, keep in mind, k-space is this abstract space. It's not physical space, but we can still say, well, a particle is somewhere in k-space by knowing what its wave function is. The energies of almost all the particles are a result of the Pauli exclusion principle. And they're much greater than they would be classically due to thermal excitation. And they're much greater than they would be classically due to thermal excitation. I'm not saying their energies are greater because of thermal excitation. I'm saying they're greater because the Pauli exclusion principle says they're much bigger than they would be if you looked at this system classically and calculated how much energy they typically have because of thermal excitation. And this is going to mean that the pressure is much, much greater than what it would be from the ideal gas law, what it would be classically, which would be given by the ideal gas law value. And this is the case where we're going to say, oh, they're exhibiting degeneracy pressure. The pressure is coming from the fact that quantum rules is a quantum mechanical phenomenon that wouldn't exist in classical physics. Question? Yes?
What do you mean by Fermi?
Which one? Right here? Third?
Fermi. What the first one is that?
Oh, sorry. The Fermi energy greatly exceeds the thermal energy. We're comparing apples to apples here. The Fermi energy, thank you, greatly exceeds the thermal energy. what happens when you're just writing, and I know what I'm thinking, and then I just get a little bit ahead of myself. Yeah. Yeah, who needs every word? So it gets tiresome. Classically, so quantum mechanically, can the particles have just any value of k whatsoever? What was the whole point of all this, right? The particles' k vectors, can they just be anywhere inside the Fermi sphere? No. If they're in a state of well-defined energy, they can only be on those grid points that we talked about before, right? Classically, can a particle's momentum be anything you want? Classically, a particle's momentum can be anything you want. And so classically, we could just define k to be the particle's momentum over h bar. And classically, the particle's momenta could be, they're not confined to the grid anymore, but we can still plot them in k space by defining k to be p over h bar. And the regime I'm talking about here is when classically the particles would all be sitting near the origin, whereas quantum mechanically the particles have been forced out here because of the only two particles allowed on each little grid point rule. And so that's the regime we're talking about here. Classically, the particles would be near the origin of k space, whereas quantum mechanically, again, they're forced out to high energy levels, high k values, because of the Pauli exclusion principle. But the other limit would be what? I'm talking about the limit where the Fermi energy greatly exceeds the thermal energy. What would be the other regime to talk about, the other limit? Stand on your head. Instead of the Fermi energy greatly exceeding the thermal energy, it'd be the other way around. If the thermal energy greatly exceeds the Fermi energy, then what happens is, because of thermal excitation, most of the particles are out here somewhere, and that's the classical regime. That, it turns out, is where the particles will behave like a classical ideal gas in that limit. So, probably worth going ahead and completing that in the notes. On the other hand, if kBT is much, much greater than the Fermi energy, then for most particles, their energy can be attributed just to thermal excitation. Most particles, we can attribute their energy to thermal excitation. Just the fact that it's hot. And in this limit, the pressure is well described by the ideal gas law. And maybe you'll get that resolved in thermal. I don't know. Jerry will have a suspicion you'll go there, so to speak, and maybe even derive that the ideal gas law holds in that limit, but we're just going to take it for granted that that is the case. Take it for granted. Yeah, if I were teaching geology, I'd have to be taking it for granted a lot. Okay, so let's now get the expression for the degeneracy pressure. we've got the Fermi energy. Let's get to where we're going with all of this. An expression for the pressure. It's a fun derivation. I like it. I like all of this stuff. I like K-space. I like thinking of an abstract theoretical space that the particles are moving in. I mean, that's my idea of fun. And I'm not joking. I do like this stuff. I hope you like it too. I command you to like it. Okay? So, degeneracy pressure. From dE equals TdS minus PdV. Y'all are in thermal. We talked about TdS and what it represents. Y'all in thermal, is that true? Is everybody in thermal? Okay. What's TdS represent? TdS is D.
We just know what entropy was.
Oh, cool. Okay, all right. Well, then reinforcement. Okay. Not going to drive this result. I'm going to tell you. This is dq, the heat flow into a little volume of gas. So if I have a little parcel of gas, or whatever, TdS is the heat flow in. Sometimes, I'm not going to bother with this, sometimes you put a little crossbar on it to say that it's an imperfect differential because it's not really, Q is not a state function. Q is not something that's independent of the path that the system takes to get to its present state. Whereas entropy is a state variable. It's something where if you know those systems, it doesn't matter how you got the system in whatever its current state is. Its entropy is independent of that, but it turns out Q is not. And then minus PdV, and we talked about that when we were talking about convection and all that sort of thing. What does PdV represent? Yeah, that's the work done by the gas on its surroundings, right? And that's another imperfect differential. It's work done by the gas on its surroundings. And I'm calling it dE here, and sometimes it'll be called U, it depends on, which book you're using kind of thing. dE, well, E is the internal energy, the internal thermal energy. So dE is, I guess we put it down here. Change in the internal energy. Right, so it says that you can change the internal energy of a little parcel by either having heat flow into it. If heat flows into it, that increases the internal energy. Or if it expands, it does work on its surroundings, and that decreases its internal energy because some of the internal energy is being used to do work on the surroundings. Sometimes people say, okay, this is like dQ in and dW by because it's the work done by the gas on its surroundings, or in general the fluid parcel. From that, we have the following fundamental relation. We have that the pressure is equal to minus the derivative of the internal energy with respect to volume, keeping the entropy constant. That's what that notation means. the derivative of E with respect to V, keeping the entropy S, I should point out, it said S is the entropy there, keeping S constant. We talked in these kinds of terms when we were talking about the convection, because we wanted to talk about adiabatic changes, no heat flow into or out of the gas as it rose or fell, as it expanded against its environment. And so that's what we're talking about here. The pressure is that there. How did I get that? By setting ds is equal to 0, right? If I set ds is equal to 0, then dE is minus P dV in that case, or ds is equal to 0. So then, in other words, if I think of dividing the change in the energy, the change in the internal energy divided by the change in the volume, but wait, there's more than one variable, so I turn that into a partial derivative, that then that'll be minus P from this relation. Just divide through by dV, and you get dE dV is minus P when ds is equal to 0. Or in other words, fancy notation, pressure is minus the partial energy with internal energy with respect to volume when the entropy is held constant. And so now it's just a matter of saying, well, okay, how do we hold the entropy constant? And again, you're kind of learning this stuff now. And so I'm just going to tell you, right, well, entropy represents, well, sometimes you say disorder, it's related to the number of ways to create the system, blah, blah, blah. In this case, keeping it at constant entropy, in other words, keeping the number of ways to create the system in question constant, well, in this case, we've got it in the ground state. We're doing this in the ground state. In other words, at t equals 0, we put all the particles in the lowest energy states they could have. How many ways are there to do that? Well, essentially, there's just, in a sense, one. Now, we could switch the particles around, but they're identical particles, so really, because they're identical in quantum mechanics, we really have to write this god-awful completely anti-symmetric wave function that has all the particles occupying all the different orbitals, blah, blah, blah. In the end, there's only one way to put the particles in the ground state. We put them, each one in the lowest energy state available. There's only one way to do that. So constant entropy means keep it that way. As I change the volume of the box, I've got my cube here, I change the volume of the box, I want to keep it so that there's still only one way to arrange the particles consistent with our description of the system. In other words, we want to keep them all in the overall ground state as we shrink the box. So all the particles stay in the same state. Now we're shrinking or expanding the box, and so the wave vectors change, but the idea would be that still, the only thing that's changing is how big the box is. It's still, the particles in the 2 wavelengths fit across the x direction. And as I expand the box, there's still a wave function where 2 wavelengths fit across that dimension. I keep all the particles in the same state, so to speak. So, to maintain constant entropy, I'll just write this out. I tried to just kind of justify this idea. To maintain constant entropy, S in other words, means to change the volume slowly enough so that the system remains in the ground state at all times. And it remains in the ground state at all times. Or in general, that each electron stays in the same state if t is greater than 0. But here we're doing t equals 0. Each electron, or fermion in general, stays in the quote-unquote same state if t is greater than 0. And so our strategy is going to be, let's find an expression for the total energy of all those particles put together, and then take its derivative with respect to volume. We'll get an expression that depends on the volume of the box, and we'll take the derivative of that expression with respect to volume. And ooh, this is going to be so much fun. Because what I want to do here is, and I do mean it, this is just really fun to me. What I want to do here is think of integrating over all the states within the Fermi sphere, really the Fermi octaves of the sphere. So I'm going to say, okay, I'm going to integrate. There's K. No sneezing. What am I going to call this little thin shell, its thickness? I'm going to call that dk. I'm going to integrate. I'm going to say, what's the energy added up of all the particles in that little shell? And I'm going to add up all the shells from k equals 0 out to k equals perifermi. I'm going to do this integral, and that will be the total energy. Right? So, give myself lots of room here. Can I erase this side right here? Okay. 2, 4, 6, 8. That's exactly right. We're going to have fun as we integrate. And it is really going to be great. So pay attention and don't be late. Because otherwise you will have to be raped as we find the energy of this state.
Which is degenerate.
Exactly, that's right, yes. All right, so the total energy of the particles is E equals the integral from 0 out to k Fermi of, so I'll write everything and then we'll say what it all means, just like we did before. H bar squared k squared over 2m times the volume of the box over pi cubed times 2 times 1/8 times 4 pi k squared dk. That's the integral we need to do. Why is that the integral we need to do? Well, for all the fermions that in k space are in this shell of radius k, their wave vector has magnitude k. What's h bar squared k squared over 2m? That's the energy of those particles, right? That's their kinetic energy. So this is the Ke of the particles in the shell. Of radius k. Now again, K space is this abstract space. It's not physical space. The particles aren't literally on this surface in real space. in K space, in this abstract space, they're living in that little thin shell. Their wave functions are defined by K's that are in that little thin shell. So there's the KE of the particles in the shell. What is V over pi cubed? What's the volume of the box divided by pi cubed? That is the also the number of per unit of K space, right? Particles per unit volume of K space. This is the number of states per unit volume of K space, right? V over pi cubed is number of states per unit volume of K space. Number of states per unit K space volume. What's another name for that? That's the of not quite. It's because we're in K space. It's the density of states. Density of states, right? So if we just say density of states, what we need is the number of states per unit volume of K space, per unit K space volume. Okay? Why is that 2 there? Yeah, that's from spin, right? Spin up, spin down. That's the spin contribution. And why is that 1/8 there? We're in the octant, only one octant. Only one octant. And what is 4 pi k squared dk? Oh, you've seen that so many times when setting up integrals. 4 pi k squared dk is not the circumference. So think of our thin shell here, right? 4 pi k squared times 1/8 is that surface area. And if I take that surface area times its thickness of the shell, the surface area of the shell times its thickness is its volume. Is its volume. 4 pi k squared dk is the K space volume of the spherical shell. So what I've done here then is I'm adding up the total energy of the particles in each spherical shell. And if I do that from 0 out to the Fermi radius, I've added up the energies of all the particles. That's the internal energy of the system. Put all those things together, right? This much kinetic energy per particle. This K space volume times the density of states is the number of states within there. And I double it because there's twice as many particles because each state can have a spin up and a spin down particle. So I'm literally adding up the energies of all the particles. Now, strictly speaking, I have to construct a sum, but we're using the fact that if there's lots of particles in there, then I can treat them as though it's continuous. I can just make the approximation that I can talk about number of particles per unit volume and not worry about slightly miscounting because some particles will, well, basically, you know, we're slightly miscounting because of the fact that particles are really discrete, but it's very slight. And in the limit of many, many particles, this becomes closer and closer to being correct. For any realistic system, this is really pretty much spot on. All right, well, I can multiply all those things together. I multiply all those things together, and it turns into, out of all that, I can factor h bar squared times the volume of the box over 2 pi squared m, because various things cancel, right? Like, what's 2 times 4 divided by 8? It's 1, my gosh, okay? So only the 2 lives on as a numerical factor, and this m can come out, it's a constant. The v can come out, it's a constant. H bar squared can come out, it's a constant. And then we've got pi over pi cubed, And so that is pi squared that can come out. And now all we've got left is the integral from 0 to k Fermi of k to the 4th dk. Right, because we've got k squared here from the kinetic energy, k squared there from volume of the shell, so we get k to the 4th. So of course now we bring up Mathematica. No, we don't. We don't bring up Mathematica. Why, what's the integral k to the 4th? I know, it's a mind blower. 1/5 k to the 5th, yeah. And then I can plug in k Fermi and 0 and get k to the 5th over 5 as the value of the integral. So this turns into h bar squared volume divided by 2 pi squared m times 1/5 k Fermi to the 5th power. I mean, look how nicely this is working out. I want to cry. It's so beautiful. So we know what k Fermi is. We have that expression that it was 3 pi squared n to the 2/3, right? So I can do this. I can say, well, this is h bar squared volume over 2 pi squared m. I'll write it as 2 times 5 times pi squared m. Pull that 5 over there. And yeah, I know it's a 10. Leave me alone. I'm going to call it 2 times 5. And then this will be 3 pi squared n to the 5/3 power. K Fermi cubed was 3 pi squared n. So K Fermi, right? K Fermi itself, I said 2/3, I was wrong. 3 pi squared n to the 1/3. K Fermi is 3 pi squared n to the 1/3, raise it to the 5th power, and I get back to the 5/3 power. This is from before. Well, now, since I'm going to take a derivative with respect to volume, let's replace n with capital N divided by the volume, because that's what it is. It's the number density in physical space. So I can say that E in the end is 3 to the 5/3 times pi to the 4/3, fun with exponents, over 2 times 5 times h bar squared over m times n to the 5/3 volume to the minus 5/3. Right? In other words, little n, number of unit volume to the 5/3, well, that's n to the 5/3 over volume to the 5/3, right? But that's the same thing as number to the 5/3 times volume to the minus 5/3. And I'm doing that because we're going to take a derivative with respect to volume. So let's write it as b to the minus 5/3. So that's the system's energy. After I do the integration and simplify, right? Because there's 3 to the 5/3, and I've got pi squared to the 5/3 over pi squared, right? And so this is pi to the 10/3 over pi to the 6/3, which is pi to the 4/3, which is where that's coming from. And there's still 2 times 5 there. Yeah, I know it's 10, but I'm going to do it that way because of the derivative we're about to take. What questions do you have? So the point of all this was to find the energy so that we could find the pressure by taking minus the EdV. Yes?
What did you write in that little triangle?
Are you talking about this bit right here?
The diagram.
Yeah, the diagram.
This here?
Yeah, what's in the little triangle? Yeah.
Oh, so this is K, the radius of this shell in K space. And this is dk, the thickness of the shell. So I set up the integral. In other words, 4 pi k squared dk is the volume of this thin shell, which I'm only showing a slice of.
So
That's-
how K is that radius?
K is this radius, which is going to vary from 0 out to K Fermi. So the whole radius of the Fermi sphere is K Fermi. And we're going to add up that result for every value of K from 0 out to K Fermi to get the total energy of all the particles. So we found the energy of the particles in this thin shell. All of this as a whole is total energy of particles with K from, and then this is being sloppy, to K plus dk, right? So it's the usual physics sloppiness, right? K ranging from K to K plus dk, which, okay, that's a little ambiguous, but you know what I mean, right? So all the ones where the wave vector, I should really get, the wave number lies between K and K plus dk. And then I add the energies of all those shells together, and that's the total energy of the whole box of particles. Okay? What other questions do you have? So now we take the derivative. Thus, the pressure is minus the EdV. Well, I can take that derivative. I know how to differentiate V to the minus 5/3. What's the derivative of V to the minus 5/3? Oh, wait, no, okay, nobody's not here. What's my mistake right here? It's a very important mistake that I made here. So this is n, right? So I'm going to replace that n, capital N, with n divided by v, but I've already got a v out here. Right? Never assume that I'm perfect, right? Much as I like to assume that, I'm too often wrong. Ask my wife, right? It's not a good assumption. Okay? So I've got v times 1 over v to the 5/3, right? So what's v over v to the 5/3? This exponent was really supposed to be, yeah, minus 2/3. It's supposed to be minus 2/3 right here. It's supposed to be minus 2/3. And that's convenient, because now I'm going to take the derivative of v to the minus 2/3. What's the derivative of v to the minus 2/3? Minus 2/3 times v to the minus 5/3. Ah! Look, when I take the derivative, I'm going to get what I had before, obviously. I'm going to get the number density back again. I'm going to get that back. Ooh. Ah. Right. I can only hope that people watching at home were like, is he going to fix that? Is he going to fix that? Is he going to fix that? Yeah, I fixed it. It's probably not worth my time to cleverly edit the video, right? Yeah. Gotta be like, And so it's v n to the 5/3, v to the minus 2/3. Just like changing the audio. So I take this derivative here, and I get all that crap, 3 to the 5/3 pi to the 4/3 over, now it's going to be 5. That's why I kept it as 2 times 5, because I'm going to bring out a minus 2/3, and that 2 will cancel that 2. Then, let's see, now I'm also, right, okay. Actually, I'll keep it as this, because I'll just do it again. 2 times 5 still. It's going to die in a minute. Give it a second. H bar squared over m times 2/3. Still n. No. N to the 5/3 times 2/3 v to the minus 5/3. But it's minus dv, so the minus 2/3 just goes 2/3 v to the minus 5/3. All right, and here I pause. Everybody agree with what I just wrote there? Okay. Because if you don't, maybe I screwed up. But I don't think I did this time. Okay, gloriously. So, okay, cool. These 2's cancel. That's nice of them. And I've got 3 to the 5/3 over 3, right? Which that can simplify to 3 to the 2/3. And so when I do all that, when I simplify, I get P is equal to 3 pi squared to the 2/3 power divided by 5 times h bar squared over m times back to the number density little n to the 5/3, because capital N to the 5/3 over capital V to the 5/3 is number of particles per unit volume all to the power of the 5/3. So little n to the 5/3. And I get 3 to the 2/3 because we've got 3 to the 5/3 over 3 to the 3/3. So that's 3 to the 2/3. And pi to the 4/3 is pi squared to the 2/3. So it's just convenient to pull the 3 pi squared together and have a little party inside those parentheses and get raised to the 2/3 power, because that's your job if you're a number sometimes, and then divide by 5, all this stuff. There it is. It's so beautiful. It gets a box around it. Here's our expression for the degeneracy pressure. There's the smiling, the crying, because it's just so beautiful. Sniffle, sniffle. What a good way to go out on the first half of class today and take a break. So, let's change this into an expression that shows how it depends on the composition of the white dwarf, because after all, in the end, we're talking about white dwarfs here. And for a low mass star, the white dwarf is going to be made of mostly, the sun's white dwarf it'll leave behind will be made mostly of, no, remember neutrinos will just fly out into space. Carbon 12, and then also some oxygen 16, right? Because sometimes triple alpha you get another helium coming in. So let's see how it depends on the composition. So for electrons, we have that the number density of the electrons, we'll call it N sub E, boy, that's going to be, in the white dwarf, they can sort of be thought of as, even though they were really realistically never attached, you can imagine that some of them are coming from carbon, some of them are coming from oxygen. Let's just pretend it's all coming from carbon, for example. In general, it would be the number of electrons per nucleon times the number of nucleons per unit volume All right, so if we want the number of electrons per nucleon, if we've got carbon 12, 12,6C, each carbon, if you imagine reassembling them all into carbon atoms, each carbon contributes how many electrons? How many electrons can we get? 6, right? Because there's how many protons in a carbon? 6, right? Contributes 6 electrons. And has how many nucleons? Protons plus neutrons in that carbon nucleus. 12 of them, right? And has 12 nucleons. So that would be, in this case, 6 over 12. In this case, but let's just keep it in general. In general, if I have a generic element where, remember up here, that's the atomic mass, the total number of protons and neutrons, A. Here's the generic chemical symbol. So X is just whatever the chemical, it's not xenon or anything like that, it's whatever the chemical symbol is. It's xylophone. And that's 6. Z is how many protons, right? So in general, the number of electrons per nucleon is Z over A, right? For carbon, it was 6 over 12. In general, it's going to be Z over A for whatever isotope of some element that our white dwarf we imagine to be made of. Well, conveniently enough, for oxygen, how many protons does oxygen have? 8. So it contributes 8 electrons per nucleus. And what's its atomic mass? Its atomic mass number, I should say. How many protons plus neutrons for the most common isotope? Oxygen, 16. 16. So what's the number of electrons per nucleon for oxygen, 16? It's, instead of 6 over 12, like for carbon 12, for oxygen 16, it's 8 over 16. Compare 8 over 16 and 6 over 12 to one another. They are both 1/2, right? So it actually works out, if you got a carbon-oxygen white dwarf, that factor stays exactly the same. Z over A is the same thing for both of the isotopes in it, the most common isotopes. So we're going to get Z over A for the first term, and the number of nucleons per unit volume, I claim, to a good approximation, is the mass density divided by the mass of a hydrogen nucleus, really the mass of a proton. Because the mass density is the number of kilograms per cubic meter, and each nucleon has about the mass of a proton. So to a good approximation, mH is kilograms per nucleon. So if I take kilograms per cubic meter and divide by kilograms per nucleon, that's how many nucleons there are per cubic meter. So rho over mh is a good approximation to that second term there. Here we're using that mh is approximately the mass of a proton, is approximately the mass of a neutron, so we can use mh as a good stand-in for the mass of a nucleon, even though it varies a little bit. Really, too, if you had taken the binding energy of the nucleus into account, that would mess things up a little, but only a little bit. The binding energy is always small compared to the total mass energy of the nucleus. So that's a great approximation, more than good enough. And so we get to write that for electron degeneracy pressure for our white dwarf, it's going to be 3 pi squared to the 2/3 divided by 5 times h bar squared over the mass of the electron, because m is electrons in this case. And then it's going to be square brackets z over a times rho over mh, all that to the 5/3 power. Draw a box around that. And so, in other words, the good thing about this is, well, how would we figure out rho? How would we estimate rho? Now, really, it's the local mass density, which varies. Rho varies inside the white dwarf. So the degeneracy pressure varies with radius. It needs to, because there needs to be a pressure gradient, because just like anything else, if the white dwarf's in equilibrium, why, in every layer, there's a balance between the inward pull of and the outward push of. And for there to be an outward push of pressure, the pressure can't be constant, because the pressure push comes from the pressure being lower on the bottom of the layer. Sorry, stop it. Higher on the bottom of the layer than it is on the top of it, so that there's a net outward force. So the pressure and density both increase towards the center. Rho varies inside the white dwarf, and is greatest at the center. So really, you need a detailed model to actually calculate the white dwarf's electron degeneracy pressure as a function of radius. But as an average value, we have rho average. What would I do to figure out the average density of that white dwarf? It's the same thing I do to figure out anything's average density. Why, I would take the of the white dwarf and divide by the of the white dwarf. I would take the mass of the white dwarf and divide it by its volume, right? And then you could plug this in there and get something like an estimate of kind of, like the average degeneracy pressure inside of it. Mass of white dwarf over 4/3 pi times the radius of the white dwarf cubed. So, this is good because, and then, well, this is a half because it's made of carbon and oxygen. And we're good to go. Everything in there is numbers that we know now, and so you can figure out what would be like the average degeneracy pressure on some of them. It'll be less towards the surface and more towards the center, and the average would be just take the mass over the volume to get the mass density. That's why it'd be worth replacing the number densities with that. Give us that expression. Now, ultimately, fundamentally determined by the number density, but the number density is equal to that other combination we have there. What questions do you have? Other than, could this be any more glorious? To which the answer is no, it could not be. It could not be. All right. So, check this out. Note, P is a bunch of junk, which we'll just all put together into a big K, some constant, all this stuff, we're going to just call that capital K, times, well, and it's also got, it's all this stuff to the 5/3 power is capital K, times rho to the 5/3 power. Rho to the 5/3 power. So a degenerate gas behaves as a fancy word we met when we were talking about convection. We talked about an adiabatic gas being a polytrope. It behaves as a polytrope. You know, if I ever repair it, I'm going to teach it to say, wants a trope, or something like that. Anyway, a polytrope with polytropic index 5/3. It's, in other words, it depends on the density to the 5/3 power. We say it's a polytrope with polytropic index 5/3. Remember, we called that gamma. No, you don't, but review, okay? Gamma equals 5/3. Just like an adiabatic monatomic ideal gas, adiabatic monatomic ideal gas. That should be like a song. Did you ever hear the like Purple People Reader song? I never heard that before. Or back in the '60s. Yeah, it's a song where he meets this alien and it was a one-eyed, one-horn flying purple people eater. One-eyed, one-horn flying purple people eater. So it was a polytrope, just like an adiabatic monatomic ideal gas or something. I don't know, but anyway. However, there's a big difference. An adiabatic monatomic ideal gas still obeys the ideal gas law, but here, nope. The pressure only depends on the density, not on the temperature. However, here, the ideal gas law does not apply. It only depends on rho, and essentially, it's a lie, it depends slightly on T, not on T. That's the big deal about the degenerate gas we mentioned, is that it doesn't depend on the temperature. The degeneracy pressure doesn't depend on the temperature. It's a bit of a lie because as you raise the temperature, some of the electrons will step a little bit outside of the Fermi surface, raise the temperature, and a few of the ones near the Fermi surface move to just outside of it. The ones deep down can't go anywhere. Why can't the ones deep down go anywhere as I raise the temperature? If I raise the temperature, that's going to cause particles to get additional energy. How come an electron down here can't move to another state a little distance away from it in K-space? Already occupied, right? All these states are already fully occupied with electrons. So I raise the temperature. Only the ones near the Fermi surface have anywhere to go. These states out here haven't been occupied yet. So if you're near the Fermi surface, you can hop outside the Fermi surface a little bit as you raise the temperature. Okay, but you didn't really raise the particle's energy that much. It already had this much squared times h bar squared over 2m energy. I move it a little further away, its energy just increased a little bit. So the pressure has changed very little compared to what it would have been at t equals 0. So to a good approximation, as long as the Fermi energy is much bigger than kT, then even at non-zero temperature, okay, there's some particles living a little outside the Fermi surface. They're not moving much faster than they were before. The pressure has hardly changed at all. So we make the approximation that the degeneracy pressure doesn't care about the temperature. And then we get fun things like why when helium burning begins in the core of a low mass star, the nuclear reactions, what's that going to do to the temperature? It's going to increase the temperature, but the core is degenerate. So what happens to the electron degeneracy pressure as a result? Stays the same, to an awfully good approximation, stays the same. And so the core cannot expand and take up the energy being released by those nuclear reactions. And so temperature goes up. What's that do to the reaction rate? Increases it. What's that do to the temperature? Increases it. What's the reaction rate? Increase, and then we get a flash. Exactly, right? Because it's degenerate. Because it's degenerate. But eventually so much energy has been released, the temperature gets so high that there's so much energy that even these guys down here can be like put way over here in some unoccupied state. Why everybody practically moves outside of the Fermi surface because the temperature is so freaking high that the thermal energy is much larger than the Fermi energy. And in that case, why rather than behaving as a degenerate gas, they behave as a classical ideal gas, right? How many two for that matter? Yep, ideal gas, and then the core can expand and all that kind of goodness because now the pressure starts depending on temperature. Now, strictly speaking, it's always degeneracy pressure, but we really reserve the term for when we're in the situation that the Pauli exclusion principle is kind of running the show. Quantum mechanics always describes the correct expression for the pressure, but at high enough temperatures, the ideal gas law is a great approximation. Similar to the way, is there some speed at which relativity starts being valid and before that it's classical? Well, no, I mean like, so if I'm moving around right here, is my kinetic energy 1/2 mv squared, or is it really the relativistic expression? Oh my God! No, it isn't. It's the relativistic expression.
It's an approximation.
The 1/2 mv squared is just an approximation that works when you're way lower than the speed of light. The relativistic expressions are the ones that are always right, no matter how fast you're going. But at low speeds, 1/2 mv squared plus mc squared, the rest energy, becomes a great approximation to the energy. Right? Same deal here. The quantum mechanics always rules, but in the right regime, you can get away with classical mechanics. Okay? All right. So now, let's talk about, well, first of all, what questions do you have? Here's my question for you. Shall we talk about the maximum upper limit for the mass of a white dwarf that might be named after some famous Indian physicist whose name pronounced properly is? Exactly, right? Let's talk about it, right? And this is one of those things, right? So when I was in high school, I read about it, and then I learned how it really works. And it's like, I always like those moments, right? So let's talk about that. But first we'll need what we call the mass-volume relation. We'll find that the mass times the volume of a white dwarf is a constant. And if it always held, well, that would mean the higher the mass, the smaller the volume, And at first it would imply that the white dwarf could just shrink and shrink and shrink as much as you like. But eventually that implies that the electrons would be moving at speeds comparable to the speed of light, and that changes how the pressure works. And that's what gives rise to the... Yes, exactly. Yes, okay. So, the mass volume relation. Our intuition is usually if I add mass to something, it gets bigger. White dwarfs, nope, it gets smaller. If I add mass to a white dwarf, it physically shrinks in size because it turns out that in order to balance the extra gravity, to kick up the pressure in order to balance the extra gravity, it has to shrink in order to get the electrons to move faster and do that. So the mass volume relation. Let's use the equation of hydrostatic equilibrium to, under the unrealistic assumption of constant density, to obtain an estimate of the central pressure. Use the equation of hydrostatic equilibrium right? Remember when we were studying the equations of stellar structure, that was the first one we came up with. Use the equation of hydrostatic equilibrium under the unrealistic assumption of constant density. But this is one of these, so-called back-of-the-envelope calculations here. Under the unrealistic assumption of constant density, we know it can't be. It has to get denser towards the center. Under the unrealistic assumption of constant density, to obtain an estimate of the central pressure. Now, back of the envelope, it won't be right, but it'll be, order of magnitude, right? An estimate of the central pressure. Remember that the equation of hydrostatic equilibrium was that the PDR was equal to minus rho times the acceleration due to gravity, which in turn is going to be g m of r over r squared, right? Here I am. Here's the whole radius, capital R of our white dwarf. Here I am. Inside it and some radius little r. M sub r is how much mass is inside that radius. And remember, gravity acts as though all the mass interior to you in a spherically symmetric situation were concentrated at the center. And so the acceleration due to gravity would be g m of r over little r squared from Newton's law of gravity. So we get minus g m sub r, mass interior to radius r, rho over r squared. Are you buying what I'm selling so far? Okay. Now, no approximations here, other than, okay, it's really described by general relativity. Okay, but, gravity's right. Same question as before. Is the trajectory of this racer correctly described by Newton's law of gravity or by general relativity? By general relativity. But we can get away with Newton's law of gravity under these conditions, right? That's kind of thing to keep in mind. Plus, I made a mess on the floor. Okay, anyway. So, all right, here's where we use the unrealistic assumption of constant density. So m of r will be 4/3 pi r cubed rho, right? Volume interior to radius r times that assumed constant density will be the mass interior to radius r times rho. Right? M of r has rho in it. Rho has rho in it because how could rho not have rho in it? Over r squared. So this turns into minus 4/3 pi g rho squared r, because this r cubed over r squared leaves an r, and there's a rho squared there. So if the density were constant, then dp dr would be minus 4/3 pi g rho squared r. And I want the eraser, but what did I do? I threw it over here. Okay, so certainly right. And yet, it was all for a good cause, education, to get you to say, well, actually, it's described by general relativity. Yeah, next chapter, we'll write down the Schwarzschild metric, and then you can calculate the trajectory. Well, okay, anyway, nothing crazy. Well, we will show cool stuff later. Okay, anyway, so with capital R being the stellar radius, 2, 4, 6, 8. Now it's time to integrate. We'll integrate to PDR. So the integral from little r equals 0 to capital R of dp dr, right? Well, like any self-respecting function, and even ones that have no self-respect, if you integrate their derivative, you get the function. And so this will be p of the upper limit minus p of the lower limit. So p at the surface of the star, well, actually, let's do this. I'm going to integrate minus dpdr because of the fact that it's dpdr is minus all that stuff. So I'm going to say minus dpdr is what I'll integrate, in which case I can flip them to our limits. And so this will be p at radius r minus p at radius capital R, because with the minus sign, I flip the limits. Being equal to,
Why would, sorry,
what's that?
why would it not be 0 p of 0? Or,
Oh, sorry. You're absolutely right. So I'm just, yeah, I really wanted to go little r, big R, just generic. Sorry. Absolutely right. Thank you for pointing that out. See, following the principle that I'm not perfect. I like it. I mean, I don't like it, but I have to accept it. Yeah. I like you doing it. I don't like not being perfect. Right. Okay. None of us do. All right. Anyway, so when I do this integral here, I'm integrating 4/3 pi g rho squared, 4/3 pi g rho squared, integral from little r to big R of r dr. Because we have rho is supposed to be constant, I can pull it out of the integral, I'm just integrate r dr. Wow, we sure are getting a lot of integrals where we don't need Mathematica today. I was not happy with something.
since we put the limits.
Yeah, so minus dpdr here is the stuff without the minus sign in front.
Yes.
Yeah.
No, I'm saying since we put the limits, would it not be big R in the bottom?
No, because of the fact that here I'm integrating minus dpdr. Oh, let me think here. Okay. Maybe. Let's see. No, it won't be because minus dpdr is what we had over there. 4/3 pi g rho squared. I'm integrating minus dpdr dr, which is 4/3 pi g rho squared, from little r to big R. We'll have to do that, right? But the integral of minus dpdr would when I put in those limits, P of little r minus P of big R. So I don't have to flip them again. What I probably should have done is just say, I'm going to take the integral from capital R to little r, dp dr, dr, and am I getting myself in trouble here? I don't think I am. I think I'm okay here. It's what I have in my notes, so it can't be wrong. Right. Are we okay with this? I think we're okay. No, okay. That's okay. I think it's okay. So, what's the integral of r? R squared over 2, right? And I'm going to plug in the limits. And so I'm going to get 2 over 3 times pi g rho squared times capital R squared minus little r squared. Yeah, I think I'm still, I think I'm okay, especially because I'm integrating. Yeah.
Sorry, I think that is correct,
Mhm.
based on the reasoning here.
Yes.
I'm just confused on the way limits have been written for that integral, why it is not from capital R to small r and that.
Okay, so I'm allowed to integrate from little r to big R, right? Doesn't stop me of minus dp dr dr. And that will be P of little r minus P of big R. It will be, right? And minus dp dr is in fact plus 4/3 pi g rho squared. So what I'm integrating from little r to big R is 4/3 pi g rho squared r. That's what I'm integrating, so there it is, integrating from little r to big R. Because this is what I'm integrating from little r to big R. Since it's minus dp dr, the result is P of little r minus P of big R. But this is the thing I'm integrating from little r to big R, and it still is over here. So I'm quite confident that I'm right now. Okay, so think about it, but I'm quite confident that I'm correct. Okay, now I wasn't right about making it 0 before, but now I'm okay with it. I'm happy with myself here. All right. What would be a reasonable thing to call the pressure at the surface of the white dwarf? That'd be 0, right? Because there it's interfacing with outer space. And so if we let P of big R be 0, then, now that won't be quite right because there's gravity there to pull things down and all that. But compared to the stuff deep down, the pressure at the surface should be nearly 0. We're making an approximation anyway. So if we say that the pressure is 0 at the surface, then we can make that 0 right there. And P of R just by itself is equal to our expression. So P as a function of R is equal to 2/3 pi g rho squared big R squared minus little r squared. That's our expression for P as a function of R. Notice if I put in little r is equal to big R, it in fact is. P of capital R is equal to 0. So then, again, with our back of the envelope estimate, the central pressure in this approximation, I'm not claiming it's correct, but this should be an approximation. In this approximation, the central pressure, P of, what value do I put in for little r to get the central pressure? 0, because at the center, little r is equal to 0. P of 0 is P sub c is approximately, because we made these approximations, well, I just put in little r is equal to 0, and all I got is the term with the capital R there, is approximately 2 over 3 times pi times g times rho squared times r squared. And this, by the way, is something that theoreticians do a lot, especially before you make a long, detailed, theoretically right calculation. You do a back of the envelope calculation like this as a check, as giving you a sense of what you should get in the end. So this is the good kind of trick to have. And now what we're going to do is set this equal to our expression for the degeneracy pressure, because why not? By setting this equal to our expression for the degeneracy pressure, why, we could solve for r and get an expression for the radius of our white dwarf. By setting this equal to our expression for the degeneracy pressure, we can estimate the radius of the white dwarf, and then we're not going to bother because it's not really what we're after, but still. We can estimate the radius of the white dwarf. And so we would say, oh, okay, 2/3 pi g rho squared r squared equals our beautiful sniff sniff expression for the degeneracy pressure, 3 pi squared to the 2/3 over 5 times h bar squared over the mass of an electron times z over a, which is a half for a carbon white dwarf, rho over the mass of a hydrogen, all to the 5/3 power. And then we can solve that for r. And I actually do that in my notes, and then I kind of realized, what did you do all that for? Because it's really kind of, so if you want to see it, oh my God, look at that, Anyway, what we want to note, okay? Let's see here. So I got rho squared here and rho to the 5/3 over here. So let's divide through by rho to the 5/3. So this is rho to the, let me get this right here, rho to the 10/3 over, where are we getting this from? It was great before. Rho squared, yes, no, but 10/3. I'm geek, so how many thirds is rho? Rho squared is rho to 1 over 3. 6, right? So rho to the 6/3 divided by rho to the 5/3 is what? Rho to the 1/3. So rho to the 1/3, right? This is rho to the 6/3. I'm going to divide by rho to the 5/3 to leave only rho on this side. Rho to the 1/3 is sitting there times r squared is equal to a constant in our approximation. That constant being everything else besides rho on that side, right? Because is 3 a constant? Is pi? Is 5? Is h bar? Is the mass of an electron? Is z for carbon? Is a for carbon? Is the mass of, are all those things constants? Are they still constants when you do this 5/3 power? Yeah. So all that stuff on that other than the rho is constant. So rho to the 1/3 times r squared is a constant. Okay? I am going to cube that. Rho r to the 6th power equals constant. It's another constant, but it's still a constant, right? I have to cube the other constant. So I just raise both sides to the 3rd power. It's really another constant, but whatever. All I care about is a constant. Okay? I mean, we assume constant density, which wasn't right, but as long as we're at it, what's a way to write rho in terms of the mass and the volume? Mass over volume. Mass over 4/3 pi r cubed. Pull that 4/3 over to the other side and make it part of the constant. So this says that the mass over the radius cubed times the radius to the 6th power equals constant. I mean, if I really want to be careful, it's another constant since I wrote it to raise to the 3rd power. And this will be yet another constant. Right, the yak, yet another constant. Oh, but wait a minute. This says that the mass times the radius to what power is a constant? Right? M/r cubed equals constant. Okay. Yet another. Like a yak, no, but whatever. It's just a constant. Right? It doesn't matter what. Okay. So mr cubed is a constant, but if mr cubed is a constant, m times 4/3 pi r cubed is a constant. But 4/3 pi r cubed is the volume. So in other words, what I was really after here is that with these approximations we've made, the mass times the volume of the white dwarf is a constant. And that's the mass-volume relation. Mass times volume is a constant, and you might object. But Dr. Harmon, you made approximations to derive this, and I would say you're absolutely right. And what do you think happens when you do it more correctly? It's still mass times volume is a constant. It survives that. So, again, I say, well, theoreticians will often start with a back-of-the-envelope calculation. And, if you pretend you're a theorist doing this, you start with the back-of-the-envelope calculation. You find, oh, well, according to this calculation, the mass times the volume should be a constant. I wonder if that holds if I do the really long-winded, detailed calculation. And then you do it, and you're like, yeah, it does. And you already got to the result you were looking for early on, and you use that to guide you to what you eventually want to come up with. So, ta-da! The mass times the volume of a white dwarf is a constant. So if I double the mass of the white dwarf, what happens to its volume? It becomes only as it was before. It only becomes half as big as it was before, right? Okay, let's think about this. I have a white dwarf in a binary system where mass is spilling onto the white dwarf from its companion. So the mass of the white dwarf is increasing as a result of this. Now, what's going to happen to the volume of the white dwarf as mass falls onto it? It's going to shrink. And if it's shrinking, why, its converting gravitational potential energy into thermal energy, radiation, but also thermal energy. So what's happening to the interior temperature of the white dwarf? It's increasing. And what if at some point, somewhere in that white dwarf, the internal temperature hits, say, 600 million Kelvin, the ignition point for carbon fusion? What do you think happens? Kaboom! Yes, that's the technical term. If I didn't really have to say kaboom, and then Earth got obliterated, but that's not friendly, right? It blows up as a type 1a supernova, right? Type 1a supernova. It's a consequence of this fact that got this mass-volume relation that says if you add mass to the white dwarf from the companion, it shrinks and heats up. And if you add enough mass, it blows up because it's degenerate. So as soon as carbon fusion begins, it runs out of control and blasts the white dwarf to smithereens. Now, there's a common misconception that I had for a long time, which was that white dwarf supernova, type 1a supernova, happens when we have talked about the Chandrasekhar limit yet, Chandrasekhar or something like that here yet. When that happens, the white dwarf collapses and that heats it up really rapidly, blows up. But it turns out simulations showed that no, actually, before it gets to the white dwarf limit, the 1.44 solar masses that's classically called, it's like when it's 1.3 something solar masses, it blows itself to smithereens because somewhere inside of it gets hot enough to blow itself to smithereens. So I had to erase my misconception and replace it with the reality, which is they actually blow up before they would collapse as a result of this. It happens before they hit that mass. So just something to realize. And it's not a carbon detonation because the burning front doesn't propagate faster than the speed of sound. It turns out supercomputer simulations show propagate slower than the speed of sound. So let's see if you remember. So it's not a detonation, it is instead a deflagration. It's a deflagration that occurs. And again, it's because of this mass-volume relation. If you add mass to a white dwarf, and it actually has to shrink in order to increase the pressure enough to get to a new equilibrium with gravity. Of course, it has to shrink. So that's step one of understanding the Chandrasekhar limit. Step two is to say, well, okay, yeah, so we keep adding mass. And this would seem to apply, as I said, seem to imply that as I keep adding mass, the volume can get as small as I like. Now, one objection would be, well, eventually it would get smaller than a Schwarzschild radius and turn into a black hole. But that's not what happens. What happens is, okay, it's getting smaller, and as it gets smaller, what's happening to the number density? It's increasing. Because you're not only adding mass, you're decreasing the volume. So the number density keeps increasing. So the Fermi radius keeps increasing, because the Fermi radius depends on the number density. And that means that the Fermi momentum keeps increasing, and that means that the speed of the particles at the Fermi surface keeps increasing. Is there a limit to how fast particles can go? Yes. Why, that would be the speed of light. So what happens is, as we'll detail next time, when the particles become sufficiently relativistic, it's no longer able to support itself. Adding mass destabilizes it past that point. It's impossible for pressure to stay in equilibrium with gravity, and instead it would, except that it would blow itself up before it gets to that point. But if you could keep it from blowing itself up, right, magic carbon that can't fuse, it would eventually collapse if you got it to a high enough mass. And in the iron core of a core collapse supernova, it can't collapse, and it can't. What, can iron serve as a nuclear fuel? No, it cannot. So in the iron core, you do get that situation where you do hit the Chandrasekhar limit, and it does collapse because of the fact that it can't hold itself up nuclear reactions wise. It collapses and releases prodigious gravitational energy, but it's not nuclear energy in that case. So, more exciting developments next time on astrophysics too. Right? So, tune in next time